So in section 1.3 here, we're going to give a real precise definition for continuity, something that we've been talking about, but we haven't really precisely defined. And then we're going to kind of move into talking about different types and finding and distinguishing between a couple of different types of discontinuities. So first, let's start with this intuitive graphical notion that is probably what you already have a good understanding of, would be my guess. So the intuitive graphical idea here basically says, if you can draw through the function at the points x equals c. So we're going to be talking about specifically continuity at a specified point. So if you can draw through that point without lifting your pen or pencil or whatever, then the function is continuous at x equals c. So this is what you probably already have a decent notion of. And you might even think about it more in a bigger picture, like an entire function is continuous if I can draw through the whole function everywhere without lifting my pen or pencil. We're honing in on continuity at a point. So this is right from your text, there is a 3-part definition of continuity that we are just simply going to translate these 3 bullets into our 3-step checklist, our 3-step checklist, that we are going to use for determining whether or not we have continuity at a point, and if we don't, we want to be able to precisely say which condition fails. So a function is going to be continuous at some value c, at x equals c, if the following 3 conditions are met. First, the function has to exist at that point. So what is f of c? Is it defined? Is it in the domain? If it is, we'll go on and test. What about the limit as x approaches c of that function? Does that exist? If it does, then we'll go on to check, are these 2 values equal? So as we go through our 3-part definition, those will be the steps that we kind of go through. All right, let's take a look at this graph we have here, and what we want to do is we want to go through and determine where there are discontinuities, and then very specifically which condition fails. So as I look at this graph, again, we're going to kind of assume here this graph, we'll just say it kind of continues off to the left in this way. So I start and I'm drawing through this graph, and it looks like the first place I come to, so maybe do this, start this over here in a different color. So, as I'm drawing through on my graph, and I start here and I'm coming through without lifting anything here, and here is the first spot where I have to lift my pen in order to keep going, and that was at x equals -3. Okay, so the places where we are going to be discontinuous. So the first discontinuity is going to be at x equals -3. So again, what we're finding here are where the function is discontinuous. So I am discontinuous at x equals -3. Now let's talk about which condition fails. And it can be more than one condition. I typically am going to go through my 3-step checklist here, and essentially the first condition that fails, it's like, okay, well, I know it's discontinuous. If you're specifically asked to go through the full thing, you certainly should be able to do so. So first part of our 3-part definition is looking at, does the point even exist? What is f of -3? Well, in this case, f of -3 doesn't exist. There's an open circle there, and that point is not defined anywhere else. So my first condition is the one that fails because f of -3 does not exist. All right, let's keep going. Okay, so if I'm continuing, I can graph, I can do this without lifting my pen or pencil everywhere until I get to right here. Once I just got to 0, I have to stop, lift my pen, and then go up here in order to kind of keep drawing. So x equals 0 is going to be my next location of a discontinuity. So x equals 0, again, is where this function is discontinuous. So let's go through our 3-step checklist here. So we start to look at, well, is f of 0 defined? And it is. F of 0 is equal to 3. Okay, so it passes my first step. Then I go on using proper notation here, FYI. I want you to be able to use proper math notation to determine what is the limit as x approaches 0 of this function. All right, well, in this case, this limit doesn't exist because if I look at the limit coming from the left and the limit coming from the right, those two values are not equal. Limit from the left is coming into 0 and the limit from the right is coming into 3, so the limit does not exist. All right, so there is failure at the limit step. Okay, so we keep drawing. Let's keep drawing through our function. Okay, so I'm drawing here, and the next place that I have to stop, lift my pen, draw this point, come back up, well, that was at x equals 2. So my next discontinuity here, is at x equals 2. All right, so x equals 2, another discontinuity. Okay, let's go through our 3-part definition. And so my first condition, step 1, is to look at, does the point exist? What is f of 2? Well, looking at the graph, f of 2, there is a point. It exists at -1. That's kind of like what I used to call the pre-calc question, right? Just where's the point? Okay, passes step 1. So then we go on to step 2. And so step 2 is going to say, well, let's investigate the limit as x approaches 2 of f of x. Well, this limit exists. As I get closer and closer to 2 from both sides on this function, my y values, the function value, is approaching 1. So the limit exists. So then I go on to step 3. And so this is where you're comparing the results that you have from step 1, where the function is defined, and with step 2, which is where the limit exists. And obviously, these two here are not equal because f of 2, where the point is defined, f of 2 was at -1, and where the limit existed was at x equals 1. So those two aren't equal, so we failed at step 3. All right, let's keep it going. Traveling along on my function, going up to the point x equals 5. I can keep going without lifting my pen or pencil. There's just kind of like a specific point highlighted there just for emphasis, I guess. And then it looks like I'm decreasing. And that dashed line there is saying a vertical asymptote. So I keep decreasing. I'm approaching this vertical asymptote, but I'm going to have to lift my pen or pencil here in order to continue drawing the function on the other side as it approaches, again, that vertical asymptote. So it looks like I have another discontinuity occurring here at x equals 6. And so this discontinuity, again, let's go through our 3-part definition. And step number 1 is determining does the point exist? What is f of 6? Well, f of 6, there is no point at x equals 6. It does not exist. So we are discontinuous. The point does not exist. But then after that, it looks like, my function is just going to kind of continue in this manner. I'll just kind of draw an arrow there. But that's going to be our last discontinuity on that. So this is kind of our introduction to the discontinuities, so you can kind of see visually it could be a hole in the graph or a vertical asymptote. So those were our first and last examples. Those are both when the first condition fails. You could have a situation like at x equals 0 where the point's defined, but then the limit doesn't exist. Kind of when you have, we might refer to that as like a jump discontinuity. And then the last example, kind of different type here, is at x equals 2, the point existed, the limit was defined, but those two values were not equal. So we have all these different types of discontinuities, and so what we want to be able to do is categorize them in a couple of different ways. So we're going to just define these two concepts, and then we'll come back and kind of look at some more examples next time. So a removable discontinuity is a discontinuity that can be removed, or it can be fixed, by defining or redefining the function at that one point. So if we were to look at this graph, like, are there any discontinuities that I could fix by simply redefining one point? And there are. If I just defined a point at -3, that would be continuous. If I, at x equals 2, just redefined that one point, that would make it continuous. So what these two have in common is both of their limits existed. So you're going to have a removable discontinuity. So removable discontinuities are going to occur. So a removable discontinuity is when the limit exists. So the discontinuity can be removed or fixed by just defining or redefining that one point. So my removable discontinuities here are at x equals -3 and at x equals 2. Well, a non-removable discontinuity then means that you can't remove that discontinuity, or you can't fix it by just defining or redefining one point. So in this kind of a situation, if you look at, for example, at x equals 0, I can't just fill in this one point. That doesn't fix the continuity. And how could I bring these two branches together? I mean, if I was to try to pull this point somehow all the way up here, well, that's going to redefine all parts of this function. Like, it doesn't just involve fixing one point. There's no way to do that. Same thing over here with this vertical asymptote. This graph keeps going and getting infinitesimally closer to that vertical asymptote, right? It keeps getting closer and closer and closer. Well, how are you ever just you can't just redefine one point and say, oh, I'm going to define that point without changing. I mean, the function was going all the way down here. You can't just put a point here without redefining, a whole infinite set of values. So you can't fix that discontinuity either. So these non-removable discontinuities are going to share the criteria. It is non-removable if the limit didn't exist. So if the limit didn't exist, you can't fix it with just one point. Can't be fixed with one point. And so in the examples that we just did here, we saw that was the case at x equals 0. And we saw that that was the case at x equals 6. So the other kind of vocabulary that I'll just sort of throw in here and kind of write off to the side is sometimes with those removable discontinuities, we might refer to those are sometimes referred to as just being like little holes in the graph. Now, whether or not there's a point defined somewhere else, yes, maybe, no, maybe at -3 there wasn't, at 2 there was, but there's just a little hole in the graph. So a removable discontinuity you might think of as just a little hole in the graph. In terms of your non-removable discontinuities, there's really two types you see there. The one at x equals 0 is what we call a jump discontinuity. So it could be a jump in the graph. You can kind of just see that occurring, right? Or it might be, and this is true at x equals 6, it might be the location of a vertical asymptote. Okay, so these are kind of the two different types of graphical situations that we could have here for these non-removable discontinuities. All right, so next time, that's your introduction to our three-step definition for continuity, as well as types of discontinuities. And so next time when we come back, we'll look at how we can look for and actually find our points of discontinuity algebraically. So if we're given the function as opposed to being given the equation of the function, that representation as opposed to the graphical representation. So that's what we'll look at next time.